So let's now consider Q-learning. So, as we've just found out, temporal difference learning differs from Monte Carlo in that it breaks up these long episodes that Monte Carlo uses into single steps. So we can actually learn on the basis of each step, so we don't need an entire complete episode to actually learn. In order to do that, rather than updating on the basis of the gain to the goal, it uses an estimate of the gain to the goal, and this process is known as bootstrapping. So at each step then, this error term that we get from how far we are from how much we need to update by depends on the next state and the next reward. So it only needs to use a single step. So it only needs to wait a single step to update the value function, which obviously has got big benefits over having to wait a lot of steps like Monte Carlo. And like I said, the way that works then is the updated value function is the previous one, and then there's a term scaled by a learning rate, which then involves the estimated new target value, take away the past value, where the actually estimated value consists of the immediate reward that we get, that we definitely know is correct, and also a component which is actually the predicted component from the next state. So rather than using state values, what we can actually also do is look at state action values, and we can use temporal difference learning to actually estimate them instead. So if you remember what the state action value is, this is then the value of the state given an action, right? Rather than just the value of the state. So we have to specify what the action is as well in order to get this value. And this is then the expectation of the gain at a particular state given we do a certain action. And we can consider here now how to calculate this update. And because we're going to discuss Q-learning, this is going to be an off-policy method. And we'll explain what that means in a second. So in this approach, then the next action that we actually do is given by the policy that we follow. Right? So we've got a certain policy in this reinforcement learning problem. So if you remember, policy means what action are we going to take, or what probability of action are we going to take given the state we have. One particular kind of policy that we could adopt is something called epsilon greedy. And epsilon greedy basically means with a probability epsilon, we do something random and we randomly choose the next action. But with probability 1 minus epsilon, we actually choose what we think will give us the biggest optimal value. So we actually choose the best action to take. However, in Q-learning, although we're going to be following one policy, we're going to use a different policy to actually choose the next action than the one we're following. So we're not going to use the behavioural policy that we're following in order to actually update. We're going to use a different approach. So we're going to update, when we do our Q update, we're going to use a policy to actually to explore, if you like, or to get to the next states. But then what we're going to do is we're going to choose, in fact, the best action when we actually do the update. And the way that update's going to work is as follows. Again, it's exactly the same kind of principle as we've seen with temporal difference. The updated Q value, which is, like I said, a Q value is the value of a state action pair, is the past value that we just had, and then there's a scaled version with a learning rate here of the first two terms here represent the predicted gain, or the predicted value of Q. Take away the past value of the past value of Q, and this business here is just so we can run the running mean, and the first term here then is the actual immediate reward we get, and this is then the predicted Q value from the next state. So when we adopt a greedy policy, what that means is we want to take the action that gives us the largest Q value, right? So if we say we've got our Q values, and this is then a value in terms of what the state is and what the next action is going to be. There's going to be a next action which gives us the best, highest possible value, and in order to, if we just took the max of Q, state and action, we just get a value out. But if we say we're going to take the argument of the maximum, what we get is it chooses the action that gives us the largest Q value, but it actually returns the action as opposed to returning the value. So if we can use this argmax of the Q value in order to return, if you like, the greedy action that we want, and then we can use that to update policy. So in other words, the action that we select by being greedy is going to be the argument of the maximum of the Q function at that state across all the actions that we could possibly take at that time. So therefore, substituting that into our update, the updated Q value is the current value scaled by the learning factor of immediate reward on that particular step, plus a discounted version. This is of the Q value, which is represented by the next state, and it's actually the best action that we found just previously. So this is getting the Q value for the best Q value for the next state. So it's choosing it from using the best action. Again, this is just to implement the running mean. So if we substitute in what the greedy action is, right, we could write it like this. Let's just look at this term here. It's just the Q term here that we're really interested in. So this is the Q of the next state with the optimal action. We can just write in A prime as being then the argument of the maximum of the Q, which basically means we end up getting the best action from this. And we're basically then evaluating the Q value for the next state and the best action for that next state, and using that as the update. But of course, what we could also do is, because we're doing it in a rather roundabout way here, we could also say, well, actually, what we care about now is the Q value here. We don't actually, this update doesn't actually use the action as such. It's actually using the best value. So all we can say is we can swap all of this out. That's what we're doing here, and say the value that we want to get from all of this is just going to correspond to, for the next state, the maximum value by choosing the appropriate action. So if we have this as a matrix, then what we do is we just choose for that particular entry st plus 1, we look across all the values we get for the different actions and just pick the biggest value, right? So we could just write the whole thing down finally like this. The final updated Q value is the past value that we had on the previous step, and then the scaled version of the immediate reward plus the best possible value, discounted value at the next step, and again take away the previous Q values just so it runs as a running average. So Qlearning then approximates finding the optimal policy using this greedy approach. Learning then is independent of the policy being followed. So we say this is an off-policy method because what it's following a policy to actually get to the next. It's finding the next action using this epsilon greedy, say, but then we always choose the best possible action when we're doing the update. And this basically works by updating these state action pairs, and after we've learned all of these things, then we can actually start exploiting it and actually find, for a given state, we can pick the optimal action to take quite easily. So just to summarise, Qlearning then directly estimates the state action pair rather than the state value. So in other words, it's not just the value of the state, it's the value of the state given an action. Qlearning uses a greedy approach to learn. It uses a different policy to actually update than the one it's using to actually to explore the space. And because it's using a different policy than the one it uses when it's running, it's called off policy, right? It's an off policy method. And we've got to just run it many times in order to get a good estimate of what the Q value of the state action pairs are. So it's a model-free algorithm. The goal is, of course, to learn this Qtable, so all these Q values, to learn policy, basically the policy of the state action pair. Normally you'd set these initially to some small random values. And the Q value is, like I said, it's representing the value of each state for each possible action that you have in that state. When we have very small state spaces, and if they're small discrete state spaces, we can actually use a table or a matrix in order to represent the Q values. It might be that when we have really big spaces, we start using functions or neural networks to actually implement these functions. In this particular case, what we see, we've got a maze. So generally in a maze, you can have 4 actions: north, south, east and west. And therefore for each of these states we'll have an associated state action value. So that's represented on this particular drawing in these 4 quadrants. After we've actually found the Q values for each of the states, so what that's saying is for each state I can look at what all 4 actions in this case have for values. If we have a greedy adoption policy, what we can do is we can go to a state, let's say we go to this state. If we then say we're going to just be greedy, then what we'll do is we'll pick the action such that the state action pair is the largest. And if we follow that, then we can actually go through and navigate the optimal path through a system such as a maze. And as we see here, it would involve, you can't see the value there, but basically that's the one with the biggest value. Going in here, we find that's the biggest. It's got a negative there, I'm not quite sure what that is. Yeah, that's got a biggest value, and we end up going into the one up there. Let's now look at the update equation in a little bit more detail, just because this is something that you're going to have to implement. So this is the updated value, then the updated Q value on the left-hand side. It makes use of the previous value plus a learning rate multiplied by, open brackets, the sum of the immediate reward going to the next state, plus this is a discounted, this is a lambda, gamma is a discounting factor. Oh, I think there's some of them have gone wrong here. Multiplied by the maximum value that we get at the next state, right? So in other words, this is the bit that's actually saying we've got to go to the next state, and then we choose the action that gives the biggest Q value, and we use the value. Again, this is taking off the previous Q value, and all of this lot's just filling in just the state, the current state, current action, and obviously this is future state. Actually doing this calculation to actually get the next state, what the maximum value is very simple to do in MATLAB. All you'd have to do is say, if this is, you've done this as a matrix, and the first element is your state, and the second element is your action. All you'd say is look at the Q value at the given state that we're interested, S prime, and choose first of all the actions, and then just pick the value which is the biggest. So that's quite an easy thing to calculate. Important thing to note then with this is that we're not using the same action that we did previously, because we're actually using the biggest to actually do the update. That's why it's off policy. That's why it. That's why it's an off policy method. The actual next action that we used was chosen on policy. So have a look at Sutton and Bartow for the pseudocode. First of all, we need to set our alpha, our learning rate. That's going to be something between 0 and 1. We need to initialize our Qtable, right? So we've got our state action pairs. We need to set them to some small random values, for example. Obviously not at the terminal value, which is going to be 0. Then we're going to have basically loops across episodes. So an episode is until it finally manages to get to the goal from the starting point. And then for each episode, right, the way we run that is we initialize randomly a starting state. And then we're going to have a loop basically over steps until it finally gets to the goal. So this is probably a while loop, or while something hasn't found the goal loop. Then what we do is we given that we're in a state S, we choose an action, right, using the policy that we've defined, for example, epsilon greedy. So, we're in state S and we choose an action. So epsilon greedy then some of the time will be random, and some of the time it's choosing what it thinks is the best action. And given the action, we look at the transition matrix, and it gives us what the next state S prime is going to be, and it also lets us calculate what the reward is from that transition from state S to state S prime. So now we've got all the values. So what we can do is we can now update, right? Now we can now update our Qtable. So updated version of the QSA state action pair is the value it was previously, plus learning rate, immediate reward, discounted best possible value for the next state S prime, and then we just take away again the previous Q value, so it runs as a running average. And then what we want to do is we want to follow the path that we're taking. So we got to state S prime in this particular step. So we then carry on from S prime and until until this basically goes all the way round until we finally get to terminal condition, right? So until we get to the end, and then we finish that episode, right? And then we just do the next episode until we've done enough episodes. So what's useful to think about, especially in terms of the Qlearning practical, and it's also going to be useful for the coursework, is to think about the following terms. We could say we want to run an experiment to see how good a Qlearning algorithm works, and in order to do that, in order to run it once so we can learn Q value values, then we need to run a certain number of trials, basically. So we need to run an episode. All an episode is going to do is going to do one pass from the start to the goal. We need to run loads and loads and loads of episodes to do a good job estimating the Qtable, right? We need to do loads and loads, and that would count as being a trial. But that's still only one particular, if you like, go at having to find out what the values are, and they all depend, of course, on how we started things initially. So what you can do is you can run lots and lots and lots of trials. Now you only need to write one trial to actually get the Qtable, but what you can do if you run loads and loads and loads of trials is you can see how they differ on different trials. How does it work sometimes better than other times? And this could be good for looking at performance, because one of the ways you can measure how well things are working is you can see how many steps the episodes are needed. across the different trials, and by running lots and lots of different trials you can start looking at things like the variance as well as the mean of how these things are working. So a trial then is just, like say, the minimum you need to do in order to estimate the Q values. So it consists of running multiple episodes, right? So you've got to, each episode is starting somewhere, it starts somewhere randomly, and it's then going all the way to the end point, to the goal. You can update on every step in that, but because you need to cover all the states in the system, obviously you need to, you need ideally have episodes that have started everywhere and multiple times, because it's going to be always doing this estimation process and building up on the basis of the last estimate it had. So a trial then will always start off with naive values. It'll always start off with let's say small Q values, and then we run, in a trial, the Qlearning multiple episodes, and all the way through it's still learning. It's at the first time you run it, it hasn't learned anything, and then it gets more and more and more until you finally end up hopefully with a good estimate of the Q values. A good way to terminate the trial is when it looks like the Q values are not improving anymore, or they've reached convergence. Okay, so this is the loop. So basically, this algorithm, as written by Sutton and Bartow here in the pseudocode, is for a single trial, right? This is a single trial that this is all doing. So for a single trial, we set up the Q values randomly, and then we do multiple episodes and we update on every single step. Now an episode then is just a single pass from where we start, which is random usually. We start from a random place until it finally gets to the goal. So it starts randomly and it'll be doing steps all around the maze until it finally gets to the goal point. So an episode is what we have in Monte Carlo. In an episode in Monte Carlo is needed every time we do an update, but here we do lots of steps within the episodes and update on every single step. And basically, here we're actually doing. So this is the loop across episodes. So here is the loop for each step. So any one particular episode is running through multiple steps until it gets to the terminal condition. And a step is just a single action, right? It's just a single. We take a single action, we get a single update, right, from the current state. And again, the way we do that, it's going to be epsilon greedy, the way we actually choose the action, and we do an update on every single step. So that's what this particular business does. This is within for each for one particular step in the episode, we're choosing an action from the current state using the policy that we're going to be using. Could be epsilon greedy. We look at the reward, we look at the next state, and we then update. So that update runs state by state.